Okay, it looks like we're recording. All right, so last time we were talking about these deformations. So in particular, if you know the equation of one surface and you want to know the equation of a different surface that has, well, a different equation, of course, but, you know, not that far off, right? Then the big idea is you can relate, in some sense, what you do to the variable in an equation to the resulting sort of geometric effect of what happens to the surface. And the rough relationship here is what we talked through last time. And roughly speaking, what you do to the variable in the equation, in some sense, the opposite happens to the surface. And the big idea, of course, is that, like, for example, if you insert an extra 2, well, the previous z coordinates aren't going to work anymore. But numbers that are half as big are going to account for that 2, and then everything, all the arithmetic kind of goes through as before. Okay, so some other examples of that. Now, let's see, I'll go ahead and zoom back in. Let's see, I can, yeah, there we go. So let's look at this equation right here. How are we going to identify the solutions to this equation? Let's see, is this rotationally symmetric? No, sadly, right? The A and the B and the C, they're all different constants down there, and I think you can't make any pair of variables here appear only in that special form. It just doesn't work. So what are we going to do about that, right? That's a hard situation to deal with, but this one, I'm all good. That's a sphere, no problem. I can understand this one from various different points of view. So all I have to recognize then is that the difference between the green equation and the orange equation is that, for example, x is replaced with x over a. And y is replaced with y over b. And z is replaced with z over c. So 3 sort of algebraic replacements that I've done. Each one of these algebraic replacements has a corresponding geometric effect, which is, again, sort of the opposite of what you do in the algebraic replacement. So replacing x with x over a, what that's going to do is it's going to stretch in the x direction by a factor of a. And likewise for the second one here, it's going to stretch in the y direction by a factor of b, and the third one will stretch in the z direction by a factor of c. And so now you just have to ask yourself a simple geometry problem, which is what happens when I take a sphere, a unit sphere, and if I stretch it as we just described. And, well, these sort of axis intersection points, all being 1 and minus 1, well, when you stretch correspondingly, they become these A's, B's, and C's, as I have indicated here. So it's a really nice technique. It allows you to take things that look vaguely familiar but not quite exactly the same and use your existing knowledge to figure out what the resulting surface is going to look like. Okay, a couple other examples, and I'm going to mostly just kind of wave my hands at these. But these two equations on the right, we don't have any rotational symmetries we can take advantage of. The A's and the B's and the C's just mess it all up. But these equations over here that look a lot like them, we've already studied rotational symmetries, right? Pretty easy arguments to make there. And so your knowledge of what these are helps you understand what these are going to turn out to be based on, well, it's just a question of how do they get stretched out. Okay. All right, and there's a few other examples in the book. I encourage you to look at those. We're going to move it along now, go into section 2.3. Oh, quick note, we're skipping section 2.2. You'll have noticed perhaps on the syllabus that there is no 2.2 entry on the syllabus. It's a topic which is mathematically really, really interesting and important, but when it comes right down to it in terms of actually, the kind of stuff we're doing in Math219, it just doesn't really fit very well. So skipping 2.2 completely. off we go now into 2.3. Y'all remember derivatives. Single variable calculus. We're going to talk about how to do derivatives in multivariable calculus. First thing to know, it's not just that there is a single kind of derivative. Right? Calc 1 was convenient in that there was a derivative, end of story. In a multivariable context, there's various different kinds of derivatives that act like derivatives in various different ways, and it's a long story, basically. So heads up about that. Don't make the mistake of thinking that once you see your very first multivariable derivative, as we will momentarily, that's what a multivariable derivative is. No, that's one of several that we're going to see. Okay. Why do we use the same word, derivative, to describe several different things? And it's because they all have something in common. All the multivariable derivatives we're going to talk about. And by the way, also, every interpretation you've ever seen of a single variable derivative, they all have this unifying feature. They relate input changes to output changes. Now, they relate, this is a deliberately vague word, relate. They relate these things in different ways, appropriate to just how they work and what their deal is. So keep a lookout for that as we move along. Alrighty. So yeah, we're going to start with partial derivatives. It's not my first choice. If I had my way, I would start differently with how to go through this. But I have an unusual point of view in that, and so I sort of recognize that the book, for example, does it in this very standard way of starting with partial derivatives. So while I recognize that there are some nice things about partial derivatives, and I am going to comply, right, and present these ideas the same way the book does, there is a significant downside to starting with partial derivatives. It kind of implicitly sort of encourages students to use partial derivatives as their cornerstone, foundational idea of how to think about multivariable derivatives. And I think that's a mistake. Partial derivatives are really not the best way to think about multivariable differentiation. There is a much more natural, powerful, really better way to think about it. And again, we'll get to that soon. So anyway, you've been warned. Don't get too comfortable with partial derivatives. Okay, so that said, let's do it. Here's the idea. We're going to take all the variables except for one. Let me do it like this. Hold them constant. Again, except for one, right? We're going to pick one variable that we're going to continue to view as a variable, but all of the other input variables, we're going to pretend that they're constants. Now, easy objection. What, you're not allowed to just pretend that they're constant. I mean, can you do that? Is that legal? They are, in fact, variables. Can you just insist that they be constant? And in fact, you can. Just keep in mind, when you say, I'm going to pretend that these are constants, then every interpretation that you make of the resulting computation only makes any sense at all if, in fact, your assumption here that these other variables are constant is actually true. Right? So this is a very narrow, limited point of view on differentiation. But it is legal to do this. So anyway, keep that in mind. And then we make the observation that if you now have a function where there's really only one variable that's actually changing and that we're treating as a variable, effectively I have a single variable function. And single variable functions, we know how to take derivatives. So go ahead. So that's the big idea. That's what we call a partial derivative. A little bit of notation before we do some examples. You'll recognize this sort of notation. It's not exactly what you've seen before, but this looks like Leibniz notation for single variable. The thing I need to draw your attention to is this symbol right there. That symbol is not a D. Very importantly, not a D. This is not optional. Yeah, you cannot use a D instead of that symbol. That would be wrong. Right, so sadly, annoyingly, hey, you've got yet another new symbol here in this what we call partial symbol that you've got to kind of practice how to draw. How to. Anyway, I know it's annoying, but you have to spend a minute there and get accustomed to it. Also very important, this is not a lowercase Greek letter delta. You see the difference in what it looks like. Again, not okay, not an acceptable alternative. So it's not a delta, it's not a D. Okay. And then while I'm here, I'll point out there is a different notation that's also used sometimes, and that is whatever variable you're taking a partial with respect to, make that a subscript. Yeah.
So that symbol is used to represent only partial derivatives?
This symbol right here?
Yes.
You would think so. Sadly, not. This symbol, while it is first used for partial derivatives, we're actually going to use it for something else later as well.
Okay. Yeah. But it's used to distinguish from just a regular derivative?
Yes, that's right.
Just a regular
Yeah. That's right. Whenever you see this instead of a D, that means it's a partial derivative. Absolutely. Yeah. Okay, so let's get our hands dirty and do one. We're going to take a partial derivative with respect to y here. Now keep in mind the deal when you take a partial derivative. The other variables, x and z, are to be viewed as constants. So if you look at this thing that we're going to take a derivative of, at a first glance, it's pretty scary looking. Multiple factors, there's a composition in one of the factors. It looks pretty annoying. You could imagine, oh man, if this were a single variable function that had all this sort of complexity in it, it would be quite a tedious calculation. But importantly, x and z are constants. That means that all of that stuff there is constant, and really all we're taking a partial derivative of then is constant times y squared. That's easy, right? The y partial, I should say the y derivative of y squared is just 2y. The multiplicative constants come along for the ride, right? But they don't really do anything because they're constants. That makes sense to everybody? That's pretty great. I nominate partial derivatives as the easiest derivatives to compute of any other derivatives that I've ever seen. They're easier than single variable derivatives because you get to pretend a huge amount of it's constant. It's totally awesome. All right, very, very convenient. And by the way, the fact that these are easy to compute is why we use them so much. One of the reasons why we use them so much. A couple other quickie examples. Now you look at this one right here, and it seems like it's going to be a hard problem. Function to the power of a function. I don't know if y'all remember logarithmic differentiation from high school, but at a glance, this kind of looks like it ought to be a logarithmic differentiation problem, but it's not, right? Because we're taking an x partial. That means x is the only variable. For the purposes of this calculation, y is constant. And that means y squared is a constant. And that means what you have here is a very simply function to the power of a constant. And it's just a power rule thing. Right? It's super easy. You just follow the usual power rule. Right? Bring down the exponent, subtract 1 from the exponent. Don't forget the chain rule, sort of derivative of the inside, that kind of business. Easy. Next one, again, also looks really hard, but now notice we're taking a z partial, which means x is constant and y is constant, and that means that this whole thing in here is just a great big ugly constant. And what's the derivative of constant to the power of variable? It's a pat single variable calculus formula, right? It's an exponential. And Boom. Is everybody happy? Okay. All right. Okay, so what I have done so far, I made up a suspicious definition. I'm just going to pretend stuff's constant that isn't, right? So highly suspicious. And I've persuaded myself and hopefully y'all that these are easy to compute, but the mere state of something being easy to compute doesn't mean that it is natural in any way, right? You can write down all sorts of definitions that are easy to compute with that don't mean anything that anyone ever cares about, right? So what we have to entertain now is the question of what does this look like? How do I visualize partial derivatives? Really, until you get a satisfying answer to a question like this, you shouldn't really believe in what you're looking at. Okay, now very importantly, and y'all heard me talk about this a lot last week, the geometric interpretation of calculus depends on what kind of a picture you're looking at. Right? So the calculus of graphs is going to be the first thing we're going to talk about. How do I interpret partial derivatives, aka calculus, in the context of graph pictures? And we're going to get an answer. It's going to be very nice. But importantly, what we get, the interpretation, geometric interpretation of partial derivatives that we conclude for graphs only applies to graphs. Right? We're going to have a totally different geometric interpretation for level sets and for another context that we'll talk about when we get there. Okay, so starting with graphs. Graphs, see it's a graph, right? I'm forming the equation that you get when you set the function equal to a new variable, in this case z. Notice this is the only multivariable graph that I can draw, right, because of dimensional limitations, and that's, again, one of the reasons that we're not super happy with graphs, right? Very limited. And here we go. Let's talk about taking a partial with respect to y arbitrarily. Okay, that being the case, this partial derivative with respect to y, we have a definition. It's a two-step process to compute a partial derivative. And each one of those steps has an existing geometric interpretation. Here we go. Step one, we're taking a y partial. That means that x has to be fixed, constant. We treat it like a constant. Let's say that constant's called a. X equals a means that I'm going to look at this plane, literally the plane where x is equal to a, right? And this is the only part of this graph I actually care about. So the original graph is a surface, but because all we care about is what's happening when x is equal to exactly that one constant value a, I really only want to know this cross-section, this x equals a cross-section of my graph. And that cross-section then is a curve, something like that. And notice, by the way, because x is constant, notice that means that cross-section, you might say it points in the y direction. By the way, really easy to mess this up. It's so easy to get confused about, let's see, x equals a, and then because x is what you just talked about, you can get confused and think that you're pointing in the x direction, or anyway, it's really easy to get it backwards, so heads up, be careful, make sure you're clear which variable is playing what role. And y partials mean x is constant, y is a variable, the plane in question is in the y direction, perpendicular to the x-axis. Everybody happy with that? Okay, cool. Now, check it out. I have this green cross-section, and it gives me the value of the function as a function of only y. Right? These heights only depend on y because x is constant. And if I have height as a function of the one input variable, which is horizontal, that's a graph. Right? So this green curve, it's a cross-section of the original graph, but it itself is the graph of this new single variable function that we're interested in. And step 2, recall, was to just take the derivative of that single variable function. We're looking at the graph of my single variable function. Taking the derivative of that single variable function, this means slope of the tangent line. So there you go. That's our geometric interpretation of a partial derivative. It's the slope of the tangent line, right? Tangent line to this curve, which itself is a cross-section of the original graph. And thus, this right here. Okay. Everybody happy? Yep.
So we're looking at this graph like on the y-z plane.
Do what now?
We're looking at this graph like on the y-z plane.
Well, it's what we're looking at is parallel to the YZ plane.
Parallel.
Yeah. That's right. So we're looking at a cross-section parallel to the YZ plane. It's not in the YZ plane because x isn't. Yeah, x is a, not 0, right? But but you're right. It's in the y direction, or you might say it's parallel to the YZ plane.
So if you were to look at a 2D representation of this graph, like flat like this,
Mhm.
you would have y as like your typical x and z as your typical y.
Let's just say y would be our horizontal axis and z would be
Horizontal and vertical, okay.
Yeah.
And then in terms of the slope is with respect to y.
Right, it's rise over the run.
Rise over, okay.
Yeah,
Right.
totally. Yeah. Yep. Everybody happy? Okay. Now, as I often do, as you all know, I have a suggested exercise, and that is to take these ideas that we just talked through for y partials. Think about how all of this would change if instead you had an x partial. So here's the punchline. The nice answer is exactly what you would hope. X partial means slope of the tangent line to the graph in the x direction, exactly as you would hope. Think through the argument that would come up with this conclusion. And again, it's just going to be an adaptation of what we just talked through, this sort of y partial argument that we just did. Just think about how to tweak it, how to adapt it, and come up with this as your conclusion. And again, as always, with all these suggested exercises, come talk to me in office hours. I'm very happy to help you if you get stuck on something like this. It's a good one to think through, though. Yeah.
So would the partial derivative with respect to x just be 0 because you fix x at a?
No. So the partial derivative of f with respect to x means x is no longer to be viewed as a constant. Now x is to be viewed as a variable, and y is going to be viewed as a constant. Yeah.
But if you're talking about that specific cross-section where you like isolated like a specific value of x, that would be 0, right?
The question, as I'm hearing it, it sounds like you're conflating two different processes. It's like you're keeping x constant as you would with a y partial, but then talking about the partial with respect to x, and that's just not a thing, right? So as soon as we say we want to compute the x partial, what that means is x is not a constant. But now y is the thing that's a constant. So you're going to get a different cross section. Does that make sense? Yeah. Okay. Now, that was our first little venture into the calculus of graphs, right? That's what partial derivatives look like in a graph setting. Now let's talk about a different interpretation of partials, the calculus of this literal picture. And I'm sure y'all recall that I call this the literal picture because with a domain and a target, I literally draw the domain, I literally draw the target. And then I visualize points coming out of the left space and going into the right space. Okay, so what does a partial derivative look like here? And it's definitely not a slope of anything because there is no anything, right? We have no surface or curve or anything of which we could even talk about a slope. So partial derivatives have a totally different interpretation here. Here's how it goes down. let's again, suppose we're talking about a y partial. That means that x and z are constants, which means we're going to fix x and z, whatever value. If x and z are fixed, that's going to define a line parallel to the y-axis. That's the line that you can move on that still has x and z remaining constant. Right? And okay, well, as we move along that line, we can talk about how much we move in the domain. Input change along that line will be some differential. Let's call it dy, because y is the thing that's changing. And as input points move, so do outputs, right? The output then will change by some amount. So what is the y partial in this context? The y partial is the thing that you do to the input change to get the output change. By the way, this is just kind of flashing back to Calc 1. Derivatives are what you multiply by input change to get output change. So there you go. Partial derivative with respect to y says, what do you multiply by this green change to get that blue output change? Is that cool? Notice no slope, right? It's not a slope at all, not even a little bit in this picture. Okay. Yeah, it's a different interpretation. This itself is unsatisfying in the sense that I can't point to it and say, there it is. That's the, it's telling me about the, some geometric aspect of my picture. It just isn't. So it's disappointing in that sense. But notice, instead, I'm interpreting the y partial by relating things that I can draw a picture of. So it's a different kind of an interpretation, but nevertheless, this is a really valuable point of view that we're going to be taking in multiple situations. Okay, moving along. Level sets. Now again, we're going to get a weird and different answer here. Common mistake is for students to look at level sets and to take a point right there, for example, and to think, oh, they asked me for a partial derivative, and then to just kind of, playing fast and loose with what kind of a picture do I have? Oh, partial derivatives are, they're slopes or whatever. And some people will insist that, like, let's say this is that slope right there, and that is completely wrong. This is complete garbage nonsense. Slope is what a partial derivative is, but a graph. This is not a graph of the function we're interested in. So does everybody see that? So make sure you don't do this, right? This doesn't make any sense at all. It's complete garbage. The way to avoid this is, again, to always sort of consciously, take an active role in always thinking consciously about, wait a minute, what kind of a picture is this? Is this a graph of my f, or is this a level set of my f? Oh yeah, it's level sets. Or is it something else? Is it one of my other kind of pictures that we have? This being level sets, we need a different geometric interpretation. Okay. All right, so here's what we're going to do. I'm going to use my favorite metaphor for level sets, which is that they are, what we use to understand topographical maps, contour lines and all that. And I like to think of each level set as representing a height on a hill that I'm doing a hike on or whatever. And so let's look at this green arrow that I've got indicated here, and what's my experience going to be if I hike in the direction of that green arrow? And well, at a glance, it looks like it's going to be pretty steep, right? I cross two whole contour lines. Let's say each contour line is 100 feet. I gain 200 feet of altitude over a very short amount of distance. That looks steep, right? So loosely speaking, the x partial is large. Now, by contrast, let's look at going in the y direction. Well, going in the y direction here, I'm still crossing two contour lines, but it takes me quite a bit more, right? That's a lot greater distance over which to still, go up the same two contour lines. That looks much more reasonable to me, right? That'll be a much gentler hike. It's longer. It'll take me a much greater distance to get up the same 200 feet, but therefore not as steep, therefore not as much slope, therefore the partial is smaller. Does that make sense? What's the scale on this? I mean, how large is large? How steep is that green? Is it like a super steep, or is it just kind of like how do I quantify this? You might ask. I need more information than's on the picture. On the picture, there's no indication of how much altitude you gain for each one of these lines. I would need to know what that altitude difference. I would also need I guess you call it a legend down here to know how far are these distances. Is this a picture of the continental U.S.? And each contour line is, 10 feet? In which case, none of these slopes are really all that much, right? Or is this a picture of my backyard and each one of these contour lines is 20 feet, in which case this is bonkers steep? Does that make sense? So these kinds of pictures, they don't really lend themselves very well to really quantifying things. But you can get a really good sort of comparative idea, and independent of the scale, what's very clear from this picture is that the x partial is greater than the y partial, at least in magnitude. Does that make sense to everybody? So I get something, right? Looking at the picture gives me some information about the behavior of the function. Not all, but some. Okay. All right. So totally different from a slope, totally different from this relationship, different pictures in different contexts. All right. Okay. So we're going to start a new topic. Talk about linear approximations. Hope y'all remember linear approximations from Calc 1. I do need to put a big asterisk on this whole conversation before we get going. I'm going to assume, for the moment, that the linear approximations in question exist. You don't need to do this when you're doing single variable calculus, because in single variable calculus there's some really convenient coincidences. Function is differentiable if you can take a derivative, and those are always simultaneously. And then, by the way, the linear approximation exists again simultaneously with if you can take a derivative, aka if it's differentiable. So super convenient. And we take it for granted as single variable calculus students because, as single variable calculus students, you haven't yet seen how, unfortunately, none of those coincidences work in multivariable. So there's going to be some nasty subtleties and inconveniences that we're going to have to address later as a result of, again, these complexities that I haven't given you any examples of yet. So for the moment, I want to sweep all that under the rug. We're going to assume that the linear approximation I'm looking for exists, and then we will deal with the scary weirdo situations in a little while, hopefully later today, time permitting. Okay. All right, so cool. Linear approximation exists. Well, golly, it's really easy to do that in single variable calculus. Here's the formula. That's the linear approximation. I'm sure y'all have all seen that before. What do we mean by saying this is the linear approximation? Well, it's the unique degree 1 polynomial that has the same value as f at the point A, and that has the same first derivative as f at the point A. So this requirement right here, we're looking for a first degree polynomial that agrees with f in value and derivative. And there is exactly one polynomial that'll do that. If the function's differentiable, again, we're going to sweep all that formality under the rug for the moment. Is that cool to everybody? Now, it's a healthy exercise to confirm this. This formula satisfies these two criteria. You may have already done this at some point in your Calc 1 experience, right? But if you haven't, I think it's a really healthy exercise. Plug in x equals a. Notice you get the same value as f. Take the derivative of this and then plug in x equals a. Notice that you get the same first derivative as f at that point a. So make sure you can do that. Again, as usual, if you have trouble, come to office hours. Happy to talk you through it. We're going to just rip off this idea for a multivariable answer to this question. So now let's suppose I have a multivariable function. Notice in input variables. Now, for the moment, still real valued. We'll deal with the vector valued later. So real valued only, but now multivariable. And I claim that this is the linear approximation in the sense that it agrees with f in value at the point A, and in the sense that it agrees with f, let's see here. I wanted to say it agrees in terms of derivative, but wait a minute, there's a bunch of different derivatives. In fact, it agrees with f for all of the partial derivatives. And again, this is something you can directly confirm, and this is another really healthy exercise, and I think it'd be a good use of your time. It's kind of really a lot like this one. You just look at the formula, take a derivative, plug in x equals a into the derivative and to the original function, and just notice that it just straight up works. Same deal here. So again, give that a shot. Make sure that you're comfortable with how that goes down. Note the analogy between the multivariable and the single variable versions. Okay. Now, this formula right here. It's kind of clunky. It's a lot to write down, goes most of the way across the page. Tedious, nobody likes that. What's nice is to notice that this part here, the part that takes up the most space, actually can be simplified in a wonderfully convenient way. Notice, for one thing, it's a sum of a bunch of terms. Notice, furthermore, that each term is a product of factors. There's these partial derivative factors, and then there's these coordinate differential factors. I call these coordinate differentials because as you move from the point A to the point X, the first coordinate started at value A1, ended at value x1. So this little x1 minus a1 literally tells you how much your x coordinate changed. Right? Okay, so this great big thing I have in blue, again, the bulk of the ugly in this formula, it's a sum of products. It's literally a dot product. Right? So it's very convenient to rewrite this, and I'm going to come down here and say I'm going to rewrite this great big blue expression, and I'm going to write it as a dot product. And you can see that this, what I have in orange here, right? These are the various coordinates. These orange factors are the various coordinates of the vector x minus a. Cool. All right, let me say it again now. We have an expression that's a dot product where one of the factors in the dot product is this natural thing, x minus a. I was at a, I moved to x. This is literally how much did my input change as a vector. So dot products being a natural construction, x minus a being a natural object, this thing here, these factors, the various partial derivatives, it is basically unavoidably then kind of natural to make them into a vector as well. this thing that I'm defining by this formula here, we call it the gradient vector. This thing, pretty natural in that it's the thing that you dot with x minus a to get the big bulk of the formula for linear approximations. You know, what other case we might be able to make for how natural it is, you know, we'll get to that later. But the mere fact that it's the thing that you dot with x minus a, that's pretty impressive. So this thing we call the gradient is natural if only for this fact alone. And with that alone, then we can rewrite our linear approximation formula, much easier formula to remember. Our linear approximation formula now is just this, but nicer. Okay. All right, everybody good? All right, this next example is very pluggy-chuggy. I mean, I'm given a function f. That's the function I'm going to use there. I'm given a point a. That's what I'm going to plug into the function. That's where I'm going to evaluate the gradient. That's what I'm going to subtract off from x. Right? And it's really just a kind of matter of computing at this point. I can take the gradient of the function f just by computing the various partials. Again, that's the definition of the gradient. It's this sort of shorthand convenience of it's a vector. That's just all the partial derivatives. I can plug in 1, 2, plug in my point A into there, and out comes then the evaluated gradient. That's what goes here. 2, 4. Everybody good? Again, x minus a. Okay, well, there's the, you can see I'm subtracting the a vector from the x comma y vector. I'm just literally plugging into that formula, and here you go. Here's your answer. This is your linear approximation formula. Just a couple of little plug-ins. Everybody okay? Now, real quick, one thing you could do. I went ahead and did it here. You could take that formula that we just plugged into, and you could kind of multiply out the dot product and kind of collect terms and stuff. And you could rewrite it as this. If you're going to be computing this like numerically, like you're going to code this into a computer you're going to compute it a couple 100,000 times, something like that, yeah, sure, go ahead and simplify the algebra, right? But in a math class, most of the time, you're not, right? So in a math class, being as this is a math class, I think it actually makes sense just to leave your answer like this, right? It's actually kind of nice to be able to see. You can, in this form, you can look and see, for example, what your evaluated gradient is because you left it in that form. Right, and you can see explicitly that you're dotting that with x minus a right there in how you write it. So I prefer to leave it like this, honestly. Unless you have a compelling reason to want to rewrite it, I wouldn't bother. Okay. Now, real quick, what we did here. Oh yeah, question.
For the gradient.
Yeah. How did I compute the partials? So keep in mind what the gradient is. The gradient, right, says I'm going to take the partials with respect to all of the input variables, right? So now in this situation, my input variables are x and y. And so what I have here, first I take the x partial of that. That gives me 2x. And then I need to take the next partial with respect to the next input variable, so the y partial of this gives me 2y.
So it's whatever your function
Yeah, it's always partials with respect to whatever your input variables are. Yeah, cool. Okay, so something about the approach that I took here, you'll notice that the first thing that I did is I wrote down the formula. You might say I had it all sort of multiplied out. I wrote down the expanded version of the formula. And then I subsequently came up with this very nice notational shorthand that saves us having to write out a bunch of stuff. And it's very convenient to have this notational shorthand. So I started with the expanded, and then I compacted it with convenience. I'm going to do the opposite with the next example, because expanding it out just makes it really nasty, and I don't want to, and I don't think you want me to either. So the notational convenience that we're going to find, that's going to be super, super convenient here, is to define this thing called the derivative matrix, df. And we'll say much more about this thing as we go along. It's defined by this structure right here. So notice, just like the gradient, it's a bunch of partial derivatives. You assemble a bunch of partial derivatives a certain way. You do have to be really careful about how you assemble it. It's really easy to disorganize it or to get it organized in the wrong way. I'll point out all of the first column. These are all partials with respect to x1. So I think it's reasonable to refer to this first column as the x1 column, because x1, the fact that I'm taking partials with respect to x1, that's the common shared sort of characteristic of all those elements. Likewise, the second column you call the x2 column, etc. Now, on the other hand, notice the first row does not have partials all with respect to a single variable. These are partials of a bunch of different, partials with respect to a bunch of different input variables. But it's always the partial of the same output variable, right? So rows have a common output variable you're taking the partials of. Columns have a common input variable you're taking partials with respect to. And you just got to memorize this and keep it straight in your mind, right? That columns correspond to input variables, rows correspond to output variables. And make sure you get it right. And if you accidentally get it backwards, effectively you'll transpose the matrix and everything goes haywire. So do be careful about that. Alrighty, and with this shorthand notation established, here's the formula for a linear approximation of a vector-valued multivariable function. It's that formula. And again, what do we mean when we say this is the formula? Well, it agrees with f in value, and it agrees with f, I'm going to say, in all of the partials. But keep in mind, there's a bunch of partials. There's a bunch of different, let's see here, let me highlight this the right way. There's a bunch of different output coordinates whose partials I need to take with respect to a bunch of different input variables. So there's, if you will, kind of n times m different partial derivatives that have to agree. Now, confirming the act of confirming that this works, right, and that this is the correct formula. Again, kind of tedious to write the whole thing out. I'm going to encourage that you do this only for a special case. Suppose that f has, let's say, 2 input variables and 3 output variables, for example. So keep it reasonable. Then there's only 6 partial derivatives to write down. I do think that's a healthy exercise as well. So I encourage you to, again, go through that, make sure you confirm that it works. And again, as always, feel free to ask me for help if you get stuck. And example, again, it's very pluggy-chuggy. Notice I'm taking x partials to get all of these. Oh, I'm sorry. Question.
What was the difference between that one and the gradient dotted with x, y, and z?
Yeah. So the gradient case, we are looking at real valued, so only one output variable, right? This case here, we're looking at vector valued, so there's a bunch of different output variables. So you have to sort of jack it up to a matrix when you have multiple output variables. Yeah. Okay, so again, this is all plug and chug right here. You take the partials with respect to the various input variables, get the various columns, assemble your matrix, plug in the point, right, where you're doing your linear approximation. And with that evaluated, that is your evaluated derivative matrix that you multiply by x minus a, add f of a, and boom, there's your linear approximation. And it's all straight up just plugging and chugging. There. Is that cool? And we are out of time. So drawing a line right there, we will pick up here on Wednesday. Oh gosh. Okay. All right. See y'all later. Let's see here.